pleased to have Professor M. Ghrce from IIT Delhi with us for conduct of the PhD pre-submission seminars of new candidates. The first candidate is Ms. Jyoti B Fulzele on the very topic Design and Optimization Strategy for Hybrid Renewable Energy System under the supervision of Dr. M. Fulzele. So, with the permission of the expert, can we begin with the presentation, sir? Yeah. So, this will be the first seminar.
Thank you, sir. Very good morning to all of you. My topic is Design and Optimization Strategy for Hybrid Renewable Energy System under the guidance of Dr. M. Fulzele. These are the content of my topics, starting from introduction. Next is the literature review. Research care. What is the problem statement and motivation of statement? Next is the objective of the research goal. Next, proposed methodology of hybrid renewable energy system, mathematical modeling, hybrid renewable energy planning or case study. Then simulation and optimization of hybrid system using Homer. Next is simulation and optimization of hybrid system using algorithm, result analysis and discussion, comparison of hybrid system cost with electricity, conclusion, feature scopes, publication and references. So first is the introduction. The role of electricity generation is one of the most important factors for the development of any country. In India, the electricity generation more or less based on conventional system which consists of large-scale thermal power plant which transmit and distribute the electricity by means of conventional grid. But this conventional grid has failed to provide reliable electricity in rural areas. In India, 70% of people living in rural village and 85% of villages are not been electrified. The rural population livelihood mainly depends on agriculture itself, and hence the rural energy planning is an important issue for the socio-economic point of view. India has got 70% of people living in rural village and 80% of people villages are not being electrified. India has got very good potential in renewable energy sector, but still the total contribution of renewable power as compared to electricity generation is very low. Due to depletion of fossil fuels and increasing pollution in the environment, people and government are now look towards an alternative sources of energy like renewable energy. The hybrid energy system is an excellent solution for the energy problems in rural areas where grid extension is difficult and not feasible. It does not depend on a single type of energy, but it is the combination of two or more different types of energy sources which combines together to give the optimum output by utilizing the natural available resources. But the design of hybrid energy system is a challenging task, as the coordination among different renewable energy sources, energy storage and loads are very complicated, and hence the optimum planning of such system is very essential before its construction. Many researchers are working in this area from last 1983 till date. Some of the most recent research work are summarized here. In 2007, a very effective technique was developed by Pradeep K. Katti and Mohan K. Khedkar. They fixed the energy flow strategy, and by using the commercial available unit sizes of PV and wind turbine, they keep the number of wind turbine constant and increase the number of PV panel until the system was balanced. In the same year, National Renewable Energy Laboratory developed a program that called as the Homer. This program simplifies the task of evaluating design of standalone and grid-connected power system using optimization algorithm. In 2007, Jyoti B Fulzele presented a paper on optimization of hybrid renewable energy system by minimizing the excess capacity. In that paper, he explored the importance of reducing excess energy in minimizing the cost of energy for renewable energy hybrid system. In 2008, K. presented a paper of optimal operational strategy for hybrid renewable energy system using genetic algorithm. In that paper, they present a comparison between optimization technique of hybrid renewable energy system using genetic algorithm and Homer. In that paper, the main objective is to maximize the power output while minimizing the total cost. In 2010, Ghrce presented a paper in that paper they discuss on the optimization strategy, sizing and operational strategy of hybrid renewable energy system with reference to minimum net present cost. Jyoti presented a paper in 2011, optimal energy mix for grid connected hybrid wind photovoltaic generation system. In that paper, they present the optimal mixed solar wind system for grid connection. In 2011, we present a paper in which they determine the system size. They formulate on the optimization problem that minimizes the total construction and operation costs subjected to maximum tolerable risks by using Homer. The detailed literature reveals that most of the researchers are work on the concept of design, optimization and simulation of delivered hybrid system. But in that analysis, it is observed that a lot of excess energy has been generated which adversely affect to maximize the cost of overall system. And hence it is essential to look into this area of section. So by considering these are the two baseline research base papers here which I selected for my research work. By considering the research gap, I set the objective of my research work. The main objective of this research work is to design an optimization of hybrid renewable energy system consisting of PV and wind that can generate and provide cost-effective reliable electricity in the rural areas of country with the constraint renewable energy fraction and minimizing excess energy. The specific objective of the proposed work are: the first objective to review the characteristics of resource input data. Second objective to determine the electricity load requirement of domestic use, commercial sectors and community-based service. Third objective to study the optimization research tool which used for the design of hybrid renewable energy system. Fourth objective is to simulate and optimize hybrid PV wind renewable energy system with battery storage applied to rural areas. Fifth objective to compare power system considering certain criteria to select techno-economical feasible system with minimum net present cost. And my last objective is to perform sensitivity analysis of power system which help to assess the effect of uncertainty or changes in the variable or will designer has no control such as average wind speed, future fuel prices, solar radiation, etc. This is the block diagram of proposed hybrid renewable energy system. It consists of PV and wind, battery and converter. The output of PV and wind is connected to charge regulator. The charge regulator controls the flow of charges from battery to load and from solar panels and wind turbines to the battery. Its role is important because the output of solar panels and wind generator are invariant in nature. The battery charge controller protects the panels and battery from overcharging and fast discharging, and it prevents the flow. Also, it blocks the flow of charges and prevents the use of natural energy sources. The output of the charge controller is connected to the converter through DC bus, and output of converter is connected to AC load through AC bus. In this system, the voltage is set at, for DC voltage is 300 volt and AC voltage is set at 230 volt. These are the different mathematical equations which use for the design of hybrid energy system. So for first design of PV generator, first of all calculate the total watt hours needed per day. After finding the total watt hours needed per day, find out the current coming from solar array which can be obtained by using equation number 1. Then calculate the number of panels in parallel as well as number of panels in series. From these three equations, the power supplied to a photovoltaic generator is calculated by using equation number 4, and similarly the equation number 5 can be used for the determination of power by using the wind turbine. For the design of battery bank, first of all calculate the capacity of battery which is capable to supply the full load, and it can be determined by using the equation number 6. Then calculate the number of batteries in series as well as number of batteries are in parallel. During battery state of charge, whatever is the energy generated by PV and wind, if it is greater than the demand, in such case battery is put into the charging condition. In such case, the state of charge can be calculated by using equation number 9. While using discharging condition, new state of charge is calculated by using equation number 10. So, by obtaining the EPV and EV generator, combining these two equations, you are combining these two quantity, you are getting the energy generated by the renewable system. These are the two research tools which I use for my research work. First is the hybrid optimization model for electrical renewable developed by National Renewable Energy Laboratory. Another is the IOGA improved hybrid optimization by genetic algorithm developed by Electrical of University of Salzburg. For optimal planning of hybrid energy system, in that study, I have done the various steps. So the first step is the site selection. Second step is the data collection and data analysis. Third step is to determine the electricity demand estimation. Fourth step is to find out the resource input data. Fifth step is the selection of system component. And sixth step, define objective function, constraints and other economic parameters. So, in the first step, in this study, in this research work, the study area which is selected for this research work is located in Dudhgaon village in Dharma Taluka in Yavatmal district of Maharashtra, India. It is belonging to Vidarbha region, Amravati region. It is located 35 kilometers towards west from district headquarters of Yavatmal, 12 kilometers from Dharwad and 635 kilometers from state capital Mumbai. The area is connected with the grid, but the supply of power is not reliable and suffering from load shedding of 5 to 6 hours of daily. And the people living in Dudhgaon village also suffered from many problems. They are still waiting for the reliable electricity, proper healthcare system, education facility and employment in the rural parts. The renewable energy potential available there are in adequate amount. All these factors motivate to select this Dudhgaon village for rural electrification. This is the map of study area. After selecting the site, next step is the data collection and data analysis. In order to size and select hybrid energy system for rural electrification, it is necessary to estimate the electricity demand of that village. For this purpose, the data collection questionnaires are given to the villagers. Objective of the questionnaire survey are to have an overview of existing living pattern of the people, to identify income class distribution for the village, to identify energy use pattern, to identify problems and limitation of the existing methods, and to identify relevant methodology for effective electricity demand estimation. In step number 3, find out the electricity demand estimation. For determination of electricity demand, here the 4 different loads I have considered. First is the household load that includes the load of lighting. Second is the commercial load, includes the load of daily need shops and floor bill. Third is the community loads, it includes the load of primary health centers, schools and street light. And last is the irrigation load which used for the water pumping in agricultural purpose. The effective demand management can be obtained by using the energy saver equipments. These are the general details of that village. Here, the table 1 shows the general details of the village with total houses of 256 with population rate of 1721. The village have one school which consisting of 8 rooms and one primary health centers of 2 rooms. The daily need shops are available in that village with quantity of 3 and one floor mill is already installed in that village. The table shows the detail of electrical appliances which used for the determination of electricity demand, and table 3 shows the operating schedule of that electrical appliances for the determination of total electricity demand. From this all data, the electricity demand has been calculated for 3 different seasons: summer, winter and rain. And by referring to this daily load profile of Dudhgaon village, the average electrical energy consumption for that village is about 725.13 kWh per day. After determining the electricity demand, next step is to find out the resource potential. In this study, there are 2 resource potential are considered. One is the solar and another is the wind. The data for solar radiation as well as wind speed are collected from these 2 websites, and from table it indicates that the average global solar radiation for the proposed site is about 5.312 kWh per meter square per day, while the wind velocity, monthly average wind velocity is about 3.22 meter per second. These are the graphical representation of solar resource input and wind resource input. By observing this figure, it is clear that the solar radiation potential is higher in the month of April and May, while during the month of July, August and September, June, July and August, September, the solar radiation potential are low. In the month of May, June, July and August, adequate amount of wind velocity are available. And hence, by combining this solar and wind resources, the system should be able to meet the energy demand under various climate conditions. After determining the resource input data, next step is the technical specification of system component. In this study, the selection of system component is based on the low cost. The selected panels having nominal voltage of 24 volt with short circuit current of 5.9 with nominal power of 190 watt peak and cost is equal to $110. The system is here the system is designed with no tracking. The wind turbine which is selected for that research work is one of the most advanced wind generators in the world, Human HWP 50. It consists of refined permanent magnet material with special copper alloy, aluminum alloy with stainless steel. Its wind energy it is highly efficient to generate power. Due to its size, it is able to place inside the nose port to reduce the air resistance and increase the efficiency. Due to its advanced technology, refined materials, its wind energy utilization factor is as low as 0.42 and generator efficiency is greater than 0.92. Its working wind speed is started from 2.5 to 25 meter per second and startup wind speed is about 2 meter per second. These are the pictorial representation of Human HWP 50 and these are the output power characteristics of selected Human HWP 50 kilowatt wind generator. For storage purpose, the battery is selected with nominal voltage of 12 volt, ampere 189, with minimum state of charge as 20% with global efficiency as 80. The converter is selected having the 150 kVA with VDC voltage of 300. This converter contains the battery charger as well as PV charge controller. After selecting the system component, next step is to define the objective function. In this study, the objective function is to minimize total net present cost and it can be calculated by using the equation number 12. The net present cost consists of capital cost as well as replacement cost and operation and maintenance cost of all components which are connected, which are used for the design of hybrid system. The total operation and maintenance cost is calculated by using equation number 13, which is equal to cost of operation and maintenance cost of all units divided by capital recovery factor, which is the function of real interest rate as well as the useful lifetime of the period. The real interest rate is calculated by using equation number 15, which calculated by using the nominal interest rate and the inflation rate. CRF is calculated by using equation number 15. By considering the other inputs which affect the power system optimization that contain the economic parameters such as project lifetime, real interest rate, discount rate and capacity shortage factor. In this study, the project lifetime is considered as 25 years. Nominal discount rate is 6.50, inflation rate is 7.38% and capacity shortage is considered as 1%. The control strategy which used for the optimization is load following as well as cycle charge. By considering all parameters, first of all the system has been simulated by using first research tool, that is the Homer. Homer is a hybrid optimization model of electrical renewable developed by National Renewable Energy Laboratory. The input information provided to Homer includes electrical load, system component, resource input data, cost, constraint, control, etc. It performs three main tasks. One is the simulation, then optimization, and next is the sensitivity analysis. This is the Homer simulated model. It consists of PV, wind, battery, and converter. In order to verify the system performance under different situations, simulation studies have been carried out. In this study, the decision variable includes the size of PV array, number of wind generators, the capacity of battery, and size of converter. In normal operation, PV and wind feeds the load demand. The excess energy generated from PV and wind is stored in battery until it reaches to its full capacity. The main intention is to produce the intention is to introduce the battery storage is to import or export the energy as per the need. By considering all this, the Homer and repeated simulation to get the feasible solution. The criteria for selecting the best component of hybrid energy system is based on minimization of net present cost, sustainability, maturity of technology, efficiency and generating minimum excess energy. The result shows that the different optimal solutions are given by the Homers. The first 8 solutions are considered for the comparison of economical power system. For comparison point of view, the first solution given by Homer is assigned as the type A architecture. Second solution which is given by Homer is assigned as type B architecture. Third solution assigned as type C architecture. Likewise, the 8th solution is assigned as type I architecture. So the first comparison is based on total net present cost and cost of energy. On the basis of comparison on total net present cost, the figure itself indicates that the from type G, H and I have produced the maximum net present cost and cost of energy also. From all that architecture, type A which generates the minimum net present cost as well as cost of energy is equal to $0.132 for the proposed site. Second comparison is based on capacity shortage and renewal fraction. By considering capacity shortage and renewal fraction as a standard constraint, all types from A to I have having the renewal fraction of 100%. The type G recorded capacity shortage of below 90.4% with renewal fraction of 100%, which is a good choice in this case. In comparing power system with such constraint, the system with higher renewable fraction and minimum capacity shortage is the good choice for the reliable power supply. But such system will require a high investment. In such case, the selection criteria is based on compromising the cost and minimizing the excess energy. So, from all that, the type A, which having the renewable fraction of 100%. And minimum net present cost is the first choice from all combination. Third comparison is based on the excess energy production. One of the constraints is considered for my objective function is the minimization of excess energy. On the basis of that comparison, it observed that among all types, type A will produce the minimum excess, among all types, type H and I produce the maximum excess energy which is above 32%. While from type A to type G will produce the minimum excess energy. Only looking into the value of excess energy only, the type G is the winner of the optimization. But as explained earlier, by considering all constraints, the type A is chosen as the best solution for the proposed site. On the basis of comparison of economical power system, the type A is chosen as the optimum cost-effective solution given by the Homer for the proposed site, which consists of 225 kW of PV, in which 13 are in the series combination and 92 are in the parallel combination, 2 wind turbine of 50 kW each, with battery bank of 6 to 5, with 25 are in the series combination and 25 are in the parallel combination, with inverter of 155 kV. The annual electricity production is about 333,869 kWh. Annual electricity production is 377,541 kWh per year, out of which solar contributes 333,869 kWh per year, which is nearly equal to 88.4%, while the wind system contributes the less energy, which is about 43672 kWh per year, which is nearly equal to 11.6%. This configuration having the lowest net present cost with minimum cost of energy is equal to $0.1323. This is the power output obtained this is the power generated by the photovoltaic system. By referring to this figure, it observed that the solar energy generated by PV system is relatively higher during the summer season due to high radiation, while from the month of June to September, solar energy generated by solar is lower. The mean output is about 38.1 kilowatt with a rated capacity of 225 kilowatt and maximum output is 193 kilowatt peak. If you have the levelized cost of energy only for the solar system is about $0.0175 per kilowatt hours. This is the output of wind turbine. Here observe that the highest power output by wind turbines is relatively higher during the month of May, June and July due to adequate amount of wind velocity are available, while for the remaining month the output of wind turbine is very low. The mean output is about 4.99 kilowatt, maximum output is 84.2 kilowatt and the levelized cost of energy is about $0.171 per kilowatt hours. After optimization process, next step is the sensitivity analysis by using Homer. Before going to sensitivity analysis, I want to clear the differentiation between optimization process and sensitivity analysis. In optimization process, we determine the optimum value of variable over which the designer have control, such as the mix of components that make up the system and size or quantity of each. While the sensitivity analysis helps to assess the effect of uncertainty over which the designer have no control, such as average wind speed or future tube values. And hence, the next sensitivity analysis can be carried out by considering three sensitivity variables as average wind speed and global solar radiation. Next sensitivity variable as PV panel cost, and third is the battery cost. So first we analyze the hybrid energy system by using first sensitivity variable as global solar radiation and wind speed. Here, by selecting the values of global solar radiation, it observed that the global solar radiation is varies from 4.044 to 6.685. Means minimum value is 4.044 and maximum value is 6.685 and average is 5.31. And hence the three sensitivity variable is considered as one is the worst condition, next best condition and one is the average condition. So by considering these three sensitivity variable, similarly for wind speed also some different values are considered. So by considering these two sensitivity variables with different values, system has been simulated by using Homer. By optimizing, Homer calculates each combination by considering the range of each sensitivity variables. And the result shows that for different values of wind speed and global solar radiation, the cost of energy changes from 0.721 to 0.108. Means for the worst condition, when solar radiation is minimum as well as wind speed is minimum, at that time the predicted cost of energy is about $0.721. While for the average, it is about 0.13. Next sensitivity variable is considered as the PV panel cost. Due to advanced material, the price of the panel may be reduced in near future, and hence, by considering PV panel cost as another sensitivity variable, the system has been simulated. Different values of panels has been checked against the cost of energy, and it observed that with the reduction of capital and replacement cost of panel, the cost of energy does not decrease as much as predicted. It is decreased from 0.13 to 0.110. The cost summary of hybrid energy system, it indicates that the cost of battery plays a major contribution in the cost of design of hybrid energy system. And hence, the next sensitivity variable is considered as the battery cost. With the reduction of battery cost, the cost of energy has great effect. It can be increased, it can be decreased from 0.13 to 0.059. After sensitivity analysis by using first research tool, the validity of Homer result has been checked by using another research tool that is called as the iHoga. iHoga is the Improved Hybrid Optimization Program developed by Electrical Engineering Department of University of Salzburg. Here the optimization is carried out by using genetic algorithm and it can be mono-objective as well as multi-objective. This is the IHOGA simulated model. All the required parameters and input data we discussed earlier are used for the simulation by using IHOGA. Here the model consists of PV, wind, battery and converter. Here also the decision variable include the size of PV panel, number of wind generator, size of battery and size of converter. This figure indicates the number of cases and expected time required for the computation of total net present cost by using IHOGA. This slide indicates the computation of total net present cost as a function of number of generations for the determination of net present cost and CO2 emission. Here, in this system, the IHOGA evaluate the 15 generations and total 26976 cases are evaluated by using IHOGA for the determination of minimum net present cost and minimum CO2 emission. The result shows that the different optimal solutions are given by using IHOGA from generation 1 to 15. For comparison point of view, the 8 solutions are considered from generation 8 to generation 15. The solution given by IHOGA for the generation 8 is assigned as the type A architecture. The solution given by IHOGA for generation number 9 is assigned as type B. For generation number 10, assigned as type C. Likewise, the 15th generation solution is assigned as a type I architecture. So again, compare the hybrid energy system for the economic power system. So first comparison is again based on total net present cost, and by referring the total net present cost, it observes that among all types, type I having the minimum net present cost as compared to the other architectures and chosen as the winner of the optimization. Next comparison is based on renewable fraction and unmet load. By considering renewable fraction and unmet load as the standard constraints, the type A, B, C, E, G, H and I having the renewable fraction below 99.05%, while type D having the maximum renewable fraction above 99.25%. Looking into the values of unmet load, here the type D recorded the minimum unmet load which is above 0.6% but below 0.8, while with the renewable fraction of 100%, with the renewable fraction of above 99.25%. And it is chosen as the winner of the optimization. But as explained earlier, by considering the renewable fraction and unmet load with maximum renewable fraction and minimum unmet load is the good choice for reliable power supply. But such architecture will require high investment and in such case the selection criteria is based on compromising the cost and minimizing the environmental pollution. And from that, type I is chosen as the winner of the optimization by considering the renewable fraction of 99%, above 99%, with minimum net present cost and cost of emission. Third parameter which is considered for the comparison is the CO2 emission. The lowest CO2 emission is one of the parameters which considered for the economic power system. By referring to this figure, it observes that the type A architecture will produce the maximum CO2 emission, while from all other architecture, type I will produce the minimum CO2 emission, and hence, from all discussion point of view, the 15 number solutions, the type I architectures, is the winner of the optimization, having minimum net present cost of $1,002,330.9 with minimum net present cost of energy is equal to $0.15 per kilowatt hours. This solution is acceptable as minimum because after 15 generation, no any better solution has been given by the IHOGA. This is the monthly and annual average electric production by the optimum system. Here the maximum energy production is by using the PV. It is about 471,848 kilowatt hours per year. While wind contribute the less energy, it is about 35,185 kilowatt hours per year. Only 1.8 the load of demand is not satisfied by the system, which is equal to 0.99%, which is considerable in this case. Almost in the all period, the energy demand can be satisfied by the hybrid system. This is the cost summary of the post-hybrid system. From cost summary, it is also highlighted that the maximum cost is contributed by PV and battery banking as compared to the other components. By using IHOGA, again the sensitivity analysis is again carried out. Again the same three variables are considered: global cell radiation and wind speed, PV panel price and battery cost. So first we analyze the hybrid system by using first variable, global solar radiation and wind speed. The result indicate that with the different values of wind speed and global solar radiation, IHOGA will produce the cost of energy which is changes from 0.3 to 0.13. This is the sensitivity analysis result for considering the sensitivity variable as the PV panel cost. With the reduction of PV panel cost, the cost of energy here changes from 0.15 to 0.11. For considering the battery cost as a sensitivity variable, with the decrease in battery cost, the cost of energy is slightly changes from 0.1 to 0.15 to 0.12. On the basis of all comparison, this is the comparative analysis of Homer and IHOGA result. Table 15 shows the optimized system comparing Homer and IHOGA. Both the model suggest the architecture consists of PV, wind, battery and converter is technically feasible for the proposed site. Homer predict the architecture consists of 225 kW of PV, 2 wind turbines of 50 kW each with converter of 150 kW. The battery size suggested by the Homer is 625, in which 25 are in series and 25 are in parallel, which produce the minimum net present cost of $90,3391.70 with cost of energy is equal to $0.1323 per kilowatt hours. While on the other hand, IHOGA predict the system which consists of 501 kilowatt of PV panels with wind turbines of 2 of 50 kilowatt each, converter of 150 kilowatt with battery numbers of 450, in which the 25 are in series and 14 are in parallel, which produce the minimum net present cost of 1002330.9. It is equal and cost of energy is equal to 0.14. On the basis of this table, it concludes that here the net present cost estimated by IHOGA is 9.87% higher than the Homer. Second comparison is based on electricity produced by the renewable system and renewable energy fraction and excess energy. Homer the system predicted by Homer will produce the total renewable energy is about 377,541 kilowatt hours per year, out of which PV contribute 333,869 kilowatt hours per year and wind contribute 43675 kilowatt hours per year. The excess energy generated by Homer is about 28.8% and renewable fraction is 100%. While on the other hand, the energy generated by the IHOGA system is higher as compared to the Homer, 507035 kilowatt hour per year due to large size of PV panels suggested in table 15. Looking into the values of excess energy is one of the constraints for the optimization. This IHOGA will produce the excess energy of 33.91 with renewable fraction of 100%. On the basis of this comparison by using table number 16, it indicates that the IHOGA will generate the excess energy of 5.81% higher than the Homer. Table 17 indicate the comparison of system cost of Homer and IHOGA. The system cost given by the IHOGA is larger as compared to the Homer because of the large size of system. Lastly, calculate the cost of energy as per the MSCB tariff structure to satisfy the load demand of Ghrce village for the site. For that purpose, according to the total consumption of Ghrce village, calculate the monthly consumption. Then, according to the tariff structure of MSCB, calculate the total amount paid to the MSCB for the given period. Here, assuming that the MSCB tariff structure rate will be increasing in near future, and it is equal to for every 5 years, increasing 5 years, the MSCB tariff structure will be increased up to the 30%. So, by considering that tariff structure, billing for 25 years are calculated. First of all, calculate the first 5 years billing, then 10 years billing, 15 years, 25 years, and 25 years billings. After that, calculate the cost of energy as per the MSCB tariff structure, and it is found it is equal to 22.838 rupees per kilowatt. This table shows the comparison of Homer, Avogadro, and MSCB cost of energy. From that result, it indicates that the cost of energy predicted by Homer is about 8.518 rupees per kilowatt hour, and it is minimum as compared to the Avogadro as well as MSCB structure. With this, it concludes that whatever be the configuration given by Homer is the best choice for for the system configuration for satisfying the load demand of the village. With this, I conclude that these are the conclusion of my research work. This work has been devoted to design optimum hybrid renewable energy system for the community of 256 households in the Ghrce village of Yatmal district, Maharashtra, India. In this study, the design and optimum planning of hybrid renewable energy system has been carried out based on electricity load, renewable sources potential, and economic of the power component. Homer is the primary software used for the optimization analysis and system design. The validity of Homer result is checked by using another software, that is the Avogadro. The result is then compared between these two. The Homer gives the optimum configuration of hybrid energy system consisting of 225 kW of PV, 2 units of wind generators, and 150 kW of inverters, which provide the lowest net present cost of $903,391.70, with the cost of energy is equal to $0.1320 for the period of 25 years. While Avogadro gives the optimum configurations of system consisting of 501 kW of PV, 2 wind turbines of 50 kW each, 150 kW of converter, and 450 battery cells with the lowest net present cost of $1,00233.9, with the cost of energy is equal to $0.15 for the period of 25 years. The excess energy predicted by Homer is less. It is equal to 28.8% with renewable fraction of 100% as compared to the energy predicted by Avogadro. On the basis of comparison, considering all constraints for economical power system, Homer gives the better result than Avogadro for the proposed site. The present cost of energy paid by the villagers of Ghrce village is lower than the value obtained from hybrid renewable energy system. Considering in this research, the cost of energy given by the hybrid renewable energy system is about $0.132 per kilowatt hour. But if the due merits are considered given to the electricity deficiency and unreliable power supply in the rural area of country, it would play a major role in the improvement of life quality of people living in the rural village. At the same time, it will also improve the quality of education, reduce firewood cultivation in-house pollution. Taking all this into consideration, this high cost should not be given concern. Thus, the implementation of hybrid renewable energy system can solve the unreliable power supply problem of the country. These are some future scope of my research work. In this study, I designed the off-grid system. This system can be expanded by comparing the current study with the grid connected. In this study, efficiency of component and temperature effect are not considered. Thus, the study includes these two parameters may be done in future. Similarly, the exact number of household and appliances used for all community services and household that can be studied by interviewing each and individual people of that villages. These are some future scope. These are the list of publications of my research work, and 2 papers are published in the international journals. First paper is Design and Optimization Strategy for Hybrid Renewable Energy System, which published in International Journal of Engineering and Research and Application, indexed in Thomas Reuters and UG Circle. Second paper is published in International Journal of Advanced Electrical and Electronics Engineering. The 3 papers are accepted for the publication, out of which first is the design of hybrid PV standalone renewable energy system of case studies is accepted for the publication in Journal of Information and Optimization Science, indexed in Taylor and Francis, Pharmaceutical, USCA, IKMO. And next paper is Design and Optimization of Hybrid PV renewable energy system is accepted for elsewhere material fluid proceedings. This is one of the papers which again accepted for publication at IIT Digital Library. These are the 2 papers which under the review, under the SCI indexing. The first review is already over. It comes under the second review, and this is the international conference. These are the references which I used for my research work.
I understand that you are not doing 2 simulators. I understand that you have gone through the 2 simulators. One is over and Europa. So you know how to use these 2 simulators. Using this, you have applied for one particular village in Maharashtra, and you are making some conclusions about how to meet the demand with minimum cost and some constraint you are using. My basic question is that why you have used these 2 simulators?
These simulators are used for the design and optimization purposes. Different optimization techniques are available.
No, I just want to, because if I say my own requirements, unless if those requirements are already available in these simulators, how are you going to incorporate this? For example, I want to include forecast, wind forecast, or solar forecast, PV forecast. Some days there is a completely shadow or shade in there, cloudy. Okay, how can I include these factors into your simulator?
These factors are also available in that simulator. We are setting that factors.
But I did not see anywhere across your presentation.
The details are included in that simulation.
No, when you are doing this kind of analysis, what is the use of all these studies? Is it for future expansion or establishment of new power system, or what is this? What is the feasibility of this study?
This study, I suggest this hybrid energy system for village electrification of the village. Because in that village, the people are suffering from unreliable power supply. So I suggest that hybrid energy system, by using that hybrid energy system, the unreliable power supply can be avoided.
So that means as of now there is no hybrid energy system.
Yes, sir.
Okay, so you are taking all some of the conditions and you are taking hybrid energy system is better in order to ensure the reliability of the power supply to that village. Is that right? So, but there are several people have made attempts as well as the literature is available on this aspect, and they are writing their own models. Whereas these two are already developed and well established and maybe available here, you have used it. But if I give my own requirements other than whatever is not available in these two software simulators, okay, how are you going to do it?
What are the requirements like?
No, whatever the requirements which are not available in these simulators, how are you going to address and what is your solution that you will give it to state electricity boards? State electricity board gives the some constraints. Okay, under these constraints which are not available in these simulators, what is your solution? Because you are the planner, you are ultimately giving a planning. It's a planning problem.
Sir, for suggesting that system, or for considering that my objective, when I am going through the research work, I observe that many researchers are working in this area. But while optimizing this system, a lot of excess energy has been generated by the designers. And I will try to minimize that excess
If
energy.
any energy is generated excess, we are happy to take it. There is no problem. As of now, we are shortfall of energy generation. Can you please mention where is the question of excess energy generation?
So if excess energy is generated, it adversely affects the cost of energy.
No, where? How it is going to have? How we are going to have excess energy? Where it is? From where it will come? What is the source of this excess energy?
Solar and wind, when we are combined together, during the high solar radiation, whatever amount of energy are generated, which satisfying the load demand and some excess energy is produced. That energy.
Excess energy, see, we need a capital investment to provide, okay, to have complete solar power. So we have some limitation. Okay, so we will not able to have complete power. Where is the question of excess solar energy? Wind. There is no wind at all. Where is the question of excess wind energy?
Restricted to the demand requirement of that village.
My question is, the village is already suffering from the shortfall of electricity. There is no reliable electric power supply, power outage, okay, for many hours. You are talking about excess energy generation. Had been there this excess energy, the village easily able to use this.
So the proposed system which is suggested, that system will produce the excess energy. And I want to try to minimize
If that is the case,
for the
no, if that is the case, how do you expect that with minimum number of PV panels, how do you expect that more energy?
so here adequate amount of PV panels are available.
At least you tell me that from where the excess energy is coming. You are assuming all plants having some demand, some generation capability. From where this excess energy is coming?
So I am talking to the present system which I suggested.
You suggested, okay. Please let me understand from where this excess energy is coming. Which source?
So during high solar radiation, summer season, whatever is the demand of that village is satisfied by using the energy generated by the resources. And after satisfying the demand, whatever is the excess energy are generated that are stored in the battery, whatever is the capacity of battery is available there, after reaching the full capacity, remaining energy, which is nothing but the dump energy, that energy are assigned as the excess energy.
So at that point of time, there is no other than PV and wind. There is no other energy sources.
So in that village, no any hydro resources are available. As well as biomass
So
potential
only
is also.
purely
That's why I am considered only the two
Purely
resources.
dependent on solar and wind. Solar and wind. So what is the rating of solar power plant?
How HOMA suggests 225 kilowatt of PV, while IOMA suggests the 501 kilowatt of PV.
This is the model. See, can you please justify this? Why HOMA is giving lower PV, IOMA is giving a higher PV? What is the reason for this?
So both software are different. Here, in both the software, here in IOMA, documentation carried out by using the genetic method. Here the documentation
See, actually on these figures, feasibility is important. So I give, okay, with this combination, I give some of my own number. Do you agree for this number? If I give, okay, let's suppose 125 I will use 3 turbines. I will use, let's suppose 200 kilowatts of converter. Battery of 500. Would you prepare to take that solution? What is the basis for this? On what basis you accept this solution? See, if the state electricity board has to accept your planning, they will also have to see feasibility whether I can able to realize this. It is not that generating a number and giving this. There should be some basis for your justification of these numbers. Okay, each software will generate some numbers. Okay, what is the feasibility? No matter whether you use an empirical algorithm or you use conventional optimization, it is immaterial for us. Because my requirement as a consumer, on what basis I can able to meet? The state electricity board has to meet the consumer demand. Okay, just giving a number, you should also supply the feasibility. How it is feasible? Your design is feasible. You are explaining. Okay, you have to set your design. Okay, customer will not purchase your design until unless it is a proven design. So they might have used some algorithms to arrive at solution. Okay, it is a paper-based solution, numerical values. But feasibility, in reality, you have several constraints. How you will able to meet this? Any logic for these numbers? Because I don't know anything about these softwares. I am looking only at the feasibility of the numbers. How can I meet this? Okay, in some cases you are providing more and more battery. What is the lifetime of this battery? What is the cost of this battery? How many hours it can take? And what is the load cycle? Have you taken any of these factors into account in your optimization or in your design? Life cycle, and what are the charging cycles? Charging of battery and discharging. What is the load cycle of the battery?
lifespan is considered 10 years of battery and minimum set of
But that depends on your
cycling.
how you are charging, how you are utilizing the energy. Okay, how fast you are pumping energy, at what rate you are taking energy, that also makes a difference. Battery material. And another thing is, most of in your this kind of plots, just you go through the one part, previous one here, previous one here. This type A to type H or type I. Okay, keep on decreasing. Okay, this is almost what is that you can notice, what conclusion you can give. Anyone can able to say that yes, with type I is better, okay, in some sense. Type A is better in some sense. So if you are looking at the cost, I always refer to the lowest cost. What is abnormality in this? Any abnormality did you see in this plot? Type I is whatever I. What is the type I in your notation, in your analysis?
This is the type.
In this analysis, if you look at the second column, okay, so what difference is there? What is the numerical value? Where is the difference you find? Fourth meets 7,000 and 4,000. states 2000, 2000. So what difference is there? Is very small.
That's very small. Difference is very small, sir.
So what is the conclusion from 8 to 8, 10,
8
and
to
11? 8, 10, 11. What conclusion you will make?
from 8 number of deflation,
It is
cost of
only
energy is high.
if I take the 7,881, another one is 4,250. So how much difference is it? Maximum of $3,000. Okay, $3,000. What makes difference when you are going for the total cost? Total cost. How much is the total cost? It's
So this is the total
10
cost.
lakhs. In a 10 lakhs. $3,000, 10 lakhs of dollars. $3,000, how much it makes? What is the percentage of this cost? It is very small. When you are going for 10 lakhs of dollars, $3,000 is how much it is? Percentage. When you are going for a power system or you are making a hybrid power system, when you are going for 10 lakhs of dollars, $3,000 will be peanuts. Reason is that when they are going for a saving of just $3,000, there is an impact on the overall system itself. What is the feasibility? For example, if you say that power consumption, savings in the losses, improving the efficiency, that is fine. But here we do not know what is the impact of reducing this $3,000. You are just looking for $3,000. But what is its impact on the technical point of view? I have seen anywhere what is the impact of this cost reduction on the figure of merit of your total system, reliability. Okay, there what is the kind of components or cost involved in the various component selection? What is its impact? You are not seeing any. You are just looking for only $3,000, which you are considering as a consumable amount.
So here we are observing that the total demand is satisfied. Means the system is technically feasible.
Technically, I did not see anywhere technically. What technically feasibility study you have made here? To the best of my understanding, after going through this softwares, you should also figure it out. That is the problem of to use any softwares. You will not able to add any of your terms. Had you been developed some of your own programs by your own simulator, any of these points you would have easily taken up. There is no problem at all. But here in this softwares you have a constraint. So what is the use? If you yourself will realize that there are constraints in the software, so what is the feasibility of your all research? You are a planner, so being a planner, you have to make all kind of feasibility studies, and then you have to give a viable solution. It must be cost effective, or if it is not cost effective, it must be more reliable, robust power system. So by going through all this, what do you claim in your thesis? Is it a reliable power system planning, or what is it? Cost effective? What is it?
I only try to present a cost-effective solution for the development.
Cost effective, when you take the cost effective, you should also take into some technical factors. What are the technical factors you have in your hand? At least you tell me what technical factors you can able to include in this software.
So here, some constraints are set here. That the funding flow is assigned, capacity shortage of 1% is set. Then Again, the academic number of academic days is assigned as 1 day. Then, simultaneously, I want to obtain the renewable fraction as 100%. This is one of the constraints.
After going through this, what is the contribution as an individual, as a researcher? What is your own contribution you make in your thesis? Is it use of software simulators you claim, or any development you claim? What is that you want to claim in your thesis? For a PhD thesis, you have to have some idea. So you have to claim something in your abstract. You have to claim something. So what is that you are planning? I did not see in your abstract in this. You are given only the outline of these chapters and other things. But normally, for the examination point of view, we need an abstract, maybe 1 page. In that, it is not an introduction. What is the work ultimately? What is the novelty of your approach? What is that you are planning to bring out in your thesis? You understood? I see. Ultimately, your thesis, when you are going to submit your thesis, this is very much required. Although you have gone through all these software simulators, paid a lot of attention as well as time in learning these softwares, but you have to bring out something new by yourself. Okay? That is your own contribution, which must reflect in your thesis. Okay? Without which it doesn't look nice if you say that this. You will actually directly claiming that Iowa is not bad, not good. Homer is very good means software. I should not directly claim like this. Suppose if you take 2 products which are available in the market, and if you say that openly, openly you decide and this is not good, means then immediately that company will come and ask you to do this.
No, so here I am suggest that the solution given by the woman.
This. So actually, if you look at this one, Ioga, okay, is that cost is more, okay, whereas Homer is cost is less. If you say Ioga is better, means you are indirectly advertising Ioga and giving a privilege in Homer. Actually, in a PhD thesis, one should not do it. What we have supposed to do it is simulator 1, simulator 2. Which simulator you cannot unless you have. If this problem goes to them, they will take your own example and they will show that you are not handling this software simulator properly. With this software also you will be able to get even much better solution than they will show you. At that point, what is your response? Please, this is very much because those are the software sellers. Okay, if they get this kind of what's called wrong impression, unless if it is really correct, okay, then they will. Otherwise, they will do all this and they will show that this is also equally capable of giving the answer, but it is inability that the system designer are unable to use properly the simulator. Many times it is possible because if we do not understand how to use simulator, there is a possibility that the final outcome will be it may be higher side or lower side, not expected value. Okay. So how are you going to claim this thing? You should consult with your supervisor and think of how you will see. It is directly claiming that Iowa is not better, Homer is very good. Would you like to claim that?
So my claim is that the solution given for the village electrification, whatever the load I have
See,
considered, for that
I am giving it directly whatever you have done. But you are telling indirectly the same thing. I am giving the what the others will understand. Okay? But what you are telling is what indirectly understanding you are putting in indirect way. But it is not advisable in any PhD thesis claiming that. Okay? So you have to think in a different context. This is one important point. And you should also think what is that you want to bring up newness that you have to say. The salient contribution of this particular thesis. It is not that I have published this paper, that paper, this journal, that journal. If you want to claim that one nowadays, journal means what is the top quality rated journal in this area, people will ask. Okay? So it may be difficult for you to show that this is published in a peer-reviewed journal. It may be difficult for you. So in that case, at least in the thesis, okay, you have to bring some newness. What is your contribution? Okay, which this contribution, even if it is 10% or 1%, 5% or 100%, it is immediate. But you have to say the significant contribution of the studies, research, okay, over the existing is very much essential. Otherwise, it doesn't look nice as it is. It should not go as a PhD thesis. There are some observations. We just talk to your supervisor, give a thought for that. Okay, how you are supposed to do it, handle this. Okay, don't claim directly these two simulators. One is best, one is bad. Okay, you should try to use some kind of relative factors, just like fuzzy. Okay, in normal case, 0 or 1, fuzzy will give small positive. Medium positive, okay, high, low. So some kind of relative quantification you should use. Don't use any numerical values. Numerical values always use impact. Okay. Don't put too much stress on the numerical factors and which will give the wrong impression of the software. Okay. Manufacturer A, manufacturer B, type A, type B. Or simulators based on some heuristic search-based simulators, okay, conventional operation-based simulators. Okay, that way you should use, but don't use the software directly because maybe these softwares are available to you in this platform. Doesn't mean that you should not put the blame on the software creators, software platforms. Okay. This is my observation. Please think what is best in whatever I have given the suggestions. You think what is best according to you should not. Okay.